Our next presentation is going to change things up a little bit. We've heard about UFS and MIPI and Uniport for the last hour. But our next presenter is going to talk to us about MIPI D-PHY, the physical layer test and measurement challenges. Raju is from Tektronix. He'll be our next presenter. And Partha is chairman of the MIPI Test Working Group. He's a system engineer for MIPI segment at Tektronix. For the past 7 years, he's been working on signal generation solutions for waveform generators and measurement solutions for real-time oscilloscopes. His current focus is on test solutions for all the MIPI D-PHY technologies. He holds He holds a U.S. patent for a method to emulate crosstalk. And prior to joining Tektronix, Partha was involved with embedded device drivers for mobile platforms and has designed algorithms for a wide range of DSP solutions. Please join me in welcoming Partha Raju.
Thank you, Roy. I do believe in Roy when he says that he did not have any influence in scheduling this as the last presentation. Okay. Thank you. I appreciate the opportunity here. So for the agenda today, let's, on the first half of the session, we will take a brief overview of the D-PHY specification and also highlight some of the newer features in version 2.0. And then in the second half, we will talk about the various test challenges for D-PHY testing in terms of the equipment, right? Equipment needs, and in terms of the software needs, and also a little bit stress on some of the device test modes the design should support to enable or make the testing easier. Okay, this is the mobile system block diagram which highlights the various specifications from MIPI for various interfaces in a mobile terminal. For example, just to mention a few, MIPI has specifications for mass storage, audio codecs, and for RFIC, just to name a few. With regard to the D-PHY, the focus is on the camera and display interfaces. And MIPI also has protocol layer specifications, namely camera serial interface, CSI, and the display serial interface, DSI. So now let's delve a bit deeper into the specification of D-PHY. So what is the minimum configuration of a D-PHY line, right? D-PHY is, as you might, few of you might know, is a forward clock system, right? At a minimum, it needs one data lane and one clock line. So there is a minimum of 4 wires, okay, data positive, data negative, clock positive, and a clock negative. And in D-PHY, each of the lanes can operate in 2 modes. The high-speed mode, which you see in red color here, it's a low amplitude, slightly lower amplitude signal, which uses NRZ type of encoding. And the receiver at this stage is the terminated mode of operation. And the toggle rate is high. It runs into gigabits, many gigabits per second. The other mode, which is the low power mode, which you see here in blue, has a higher amplitude. And in this case, the receiver is unterminated, and it has a lower toggle rate, which is primarily used for control purposes. For example, sending control commands between the apps processor and the camera, for example. And of course, this high speed is for the data traffic, for example, image data. So one more highlight was, one thing I wanted to highlight was The LP mode uses a slightly unique kind of encoding, spaced 1 hot encoding. So this is the slight distinctions between the low power and the high speed mode. Moving on, as we know, another point is the low LP mode. The lines are driven in a single-ended fashion. So you would end up having 4 states. Excuse me. Just write this too. Okay. The LP mode would have 4 states, and the stop state, which is referred to as LP11, is the default standby state in the system. In a high-speed data transmission, the system holds the lines at LP11, which is the stop state. As soon as a request for a high-speed transmission is received, it sends out an LP11 signal for a duration of TLPX, okay? And then, and the lines are driven at LP00 for a duration of HS prepare. During this time, the receiver is switching the terminations. Once the terminations are switched, it's ready to, the HS traffic is ready to be sent. It sends out, there is a HS0 region where the HS0 region is sent here, and a sync pattern is sent here during which the receiver is getting prepared for high-speed data reception. And then followed the highlighted region here in red is the HS payload. And one more option is that a clock lane, right, can operate either in a continuous mode, which is what is shown here, continuous mode, which means that it doesn't have any HS transitions, or it could also have, we could also have designs which implement a bursted clock. Okay, these are the variations the designs could bring in. Okay. Further, with regard to a few more parameters on the data and the clock timing, as we know, it is a forwarded clock system. The diagram here shows the relationship of the data with respect to the clock. The clock is in quadrature with the data, meaning that it is enabling the receiver to sample at the clock edge. In D-PHY, it is a dual data rate clock, so which means the data will be sampled both at the rising edge and the falling edge. As you know that we have many versions of D-PHY and covering a wide range of data rates. So the data to clock timing specification is actually specified in different ways for different designs or devices with different data rates. So for designs with data rates up to 1.5 gig, the timing is specified by 3 parameters primarily. The data to clock static skew, and the receiver data to hold, receiver data to clock setup time, and the receiver data to clock hold time. As the rates increased in version 1.2 and above, right, version 1.2 and version 2.0, data rates for data rates above 1.5, the timing budget is specified in the form of jitter. It's imperative to specify jitter timing parameters for higher data rates. So it is specified in the form of total jitter, deterministic jitter, random jitter for devices operating more than 1.5 gig. So timing budget essentially says that this is the minimum observable jitter with which the receiver needs to perform at the maximum data rate. That's the implication of data to timing jitter. So there are a few more additional newer elements. These are newer elements in version 2.0 of the spec. One is the half swing mode. In this case, the driver can, in this mode, the driver can, could operate in half the differential voltage compared to the default swing mode. This enables in some power saving option. This is an, in fact, the half swing mode is an optional feature. And as you know, as the data rate increases to mitigate the additional ISI introduced, we need transmit equalization in the form of de-emphasis. It has one cursor and a post cursor. Two equalization ratios are defined in the spec now currently. And this is an example plot of the de-emphasis where whenever there is a transition, this level holds at the VOD level, and a following bit to that transition is reduced in amplitude. So continuing on with further features in version 2.0, to mitigate the peak emissions in the system, SSC, spread spectrum clocking, is introduced. And the SSC parameters are actually identical to the USB spec here, which is a triangular downspreading profile of 5000 ppm at 33 kilohertz. The jitter and timing budget we saw previously, right? To supplement that, they have also defined an eye diagram. I keep getting this wrong all the time. An eye diagram, okay? And this eye diagram is actually defined at the end of a reference channel. What it means is when we are testing the transmitter, you also embed the channel and measure for this eye mask. To help aid in testing, this mask has been defined for two BER ratios, 1e power minus 6 and 1e power minus 12. So differential insertion loss has been defined even since from version 1 of D-PHY. What is new in the recent versions are that they have specified the insertion loss characteristics, and they have provided three options. One is the standard reference channel, which all designs must meet this channel. And for lower loss interconnects, a short channel is defined. And to support a very high loss interconnect, for example, chip on glass kind of applications for displays, a long channel is defined, which is a higher loss. And one more guide that has been provided in the specification is the various configuration. The table here you see is a guide for the various transmitter and receiver options available for different channels and the data rates that the configurations can achieve. This is just a guidance. Okay. So when if you guys are conversant with the different versions of D-PHY, version 1.1 of D-PHY to version 1.2, the major change was this feature, was the receiver de-skew calibration feature. Designers felt that the existing 1.1 designs had enough margin in it to push the envelope a bit further by just including an additional feature in terms of de-skew calibration, where essentially a de-skew calibration pattern burst is sent from the transmitter, and during this time the receiver kind of readjusts the skew of the clock which it's been receiving and to make more accurate decoding of the bits. All right, next. Next is this is just one slide just to highlight some of the very interesting spec parameters related to LP. LP, as you know, it has a higher voltage. It goes up to 1.3 volts. And LP has a few interesting interferences defined, whereas there are 3 interferences defined. That the receiver should be robust enough. Excuse me again. So the receiver should be robust enough to ignore all the pulses which is of this size defined by each spike, or the receiver must be able to decode the pulses even if it is wider, as wide as T-min Rx. Or another one is the peak interference. If there is RF interference specified by V and F frequencies values, it should be able to tolerate the receiver, just to make the LP receiver more robust. So this completes the first section where we talk about the spec, highlighted various parameters of the spec. Now let's take a look at the various measurement challenges you would have in testing these D-PHY designs. Okay, before that, let's just talk about the various elements of testing, right? First, to test a design, you need a test methodology, right? For example, you want to test whether you want to test in a continuous mode or in a burst mode, or whether you want to process the sync bits, or you want to process the whole payload, or you want to operate in a HSLP region. That's the test methodology, right? And then you would need the test equipment, whether it is in terms of the hardware, the probes, the accessories, and the software, okay? And the third is the device test modes. What the devices needs to support to enable in testing, right? For example, does the design have the capability to generate test patterns, whatever is needed? Can the device designs receivers have error detectors, right? These are all options which the designers should consider implementing to make the testing easier. So we're just trying to reiterate the point that test modes can make a big difference between test time and testing, making it easier, right? We know it's already complex. All right. So getting into the transmitter test challenges, we already noted that HS and LP has different terminations, right? So when you're testing your transmitter, the test equipment needs to have the capability to switch dynamically. The termination needs to switch dynamically. And if you see this diagram closely, right, there are a bunch of timing parameters, and there are, of course, 2 different modes, LP and HS. First thing we need to do is we need to decode which region you need to perform the measurement on, right? Which needs a slightly sophisticated algorithm on the scope, if you're using one, to discern these regions firstly, and then perform the measurement. And then coming to probing, right? Given that the LP and the HS receiver sees different termination, right? The probe should not load down the bus. So the probe needs to have a higher impedance probe. And in the case of mobile designs, right, you always have a challenge of access. The test point should be easily accessible, right? That's also a challenge. Always you may not have the SMA outputs which you could connect directly to the scope. Access to tight test locations is also key. And some of the other things where we need to perform timing measurements, and we need to perform measurements on both data and the clock. So we have 4 spec versions now, version 1.0 to 2.0. 2.1 is being talked about, which will be ready by the end of the year, which spans from 800 Mbps to 4.5 gig. So you need to know what equipment suits which version, or you want an equipment which covers the whole range. So those are points to think about. And newer measurements have been added in version 2.0, Eye Diagram, spectrum clocking, embedding a channel. There are new LP mode measurements. These are this is just a snapshot of the various aspects we need to consider to test a design, and the test equipment needs to support all of it to enable comprehensive test. So this is a kind of a summary slide of the TX testing. We know that this is a kind of block diagram of receiver test, transmitter test setup. As we know, there are 4 wires at a minimum. We need to test D-PHY. The 4 wires are fed to the 4 channels of an oscilloscope. That's one thing. And we know we wanted switchable termination, right? There is a termination board here, and this is actually the device under test. So based on what version of the spec you want to test today, and what spec you might want to test in the future, you may have to choose the capability of the test equipment in terms of oscilloscope capabilities, the probing capabilities, right? Just as a note, this is a picture of a termination board, right, which covers up until version 2.0, up to 4.5 gig. So the current CTS has about 50 plus tests in the suite. Okay, this is more of a summary slide here. So moving on, I think we can skip this slide. There's similar content in the after this. Coming to one of the tests is the spread spectrum clocking, right? So here in this slide, I want to highlight some of the some focus on the test modes, right? So the test described in the CTS needs us to perform the measurement at a minimum of 2 SSC cycles, which is at 30 kilohertz. The minimum is 30 kilohertz, which actually amounts to, I'm sorry again, which amounts to about 66 microseconds. So we have been testing at various designs, right? Not all designs have the flexibility to control the length of the payload, right? So in this case, you would need a minimum of 66 microseconds of the payload in test mode for us to be able to test, right? So these are some of the things which we have encountered while testing various designs. I would encourage you to keep these in mind. And if you have any other further cases related to this, I'd be happy to talk to you. Another one is the eye diagram measurement, where generally we perform it at a BR of 1e⁻⁻⁶, where we capture a very big record of about 3 million UI and perform the measurement. So the recommended and the right way to do this measurement is to perform on a continuous pattern, right? This is what you see here, the continuous stream of 3 million UI. So that gives you the most accurate representation of your design. But we know that there are old designs or previous designs which cannot stream such a length of a continuous data. So for them, the only option is to operate on bursts. Right? Multiple bursts, accumulate the result of each burst so that you get you can perform the measurement with 3 million UI. That is actually not recommended by the CTS, but in some cases it would be unavoidable, and that would not be a real representation. I think the best representation of the design would be to perform on a continuous. And some of them would like to perform the measurements at 1 e power minus 12, right? For that, to do this testing, the only way is to use additional sophisticated software in terms of extrapolation methods on the oscilloscopes, right? That's the only way. Moving on, that's the story about the transmitter. Now coming to the receiver testing, the general philosophy of receiver testing is you generate a calibrated stimulus from a waveform generator, feed it to your receiver, and see whether the reception was error-free. That's the general philosophy. So for that, what do you need? You would need a waveform generator. Talking about in terms of D-PHY, you need a waveform generator which generates data and clock, 4 lines of data, DPDN and CPCN. And of course, you would need an oscilloscope. Sorry, I'm not able to point it right. Oscilloscope for calibration purposes. So there are about 35 tests in the compliance test suite. So let's just let me just back up 1 second. So we know we need a generator to generate various kinds of stimuli for receiver testing. In the first part of the presentation, we saw there were various kinds of parameters you need, various kinds of stresses we need, various modes you need, right? The capability of the waveform generator should be to allow you to do all that to test the receiver. So I've tried to summarize in 2 slides. We have another slide on this. All the various kinds of stimuli you would need to test the D-PHY receiver. Just test this compliance test suite, you would need various. First thing is you would need to generate a high-speed mode and a low-power mode. You need a data and you either need a continuous clock or a bursted clock. You would need to be able to encode, do one heart space encoding. And you also want to control the timings. And about this test patterns, you need to have the flexibility to use the pattern you want, right? Test patterns, PRBS patterns, somebody wants to use a color bar. De-skew calibration bursts, rise time control, voltage. Essentially, I've tried to list what all we discussed already, right? If you put it in one slide, you now get a feel that there's a lot the waveform generator needs to offer to cover all the tests. Okay, there is another second slide. So we need to be able to do channel embedding, de-emphasis, all the LP mode receivers, LP mode stresses, excuse me. So traditionally, right, particularly if you talk about receiver testing, the receiver testing is generally complex than a transmitter testing, that is true. But previously it was even more complex because of the various unique kind of stresses the LP wanted. I think if you have been testing in the lab, you would know, it's very complex. Now I think I can say this, right, now now it's become slightly more easier, right? Adding these stresses, all that, it's become slightly more easier, I must say. So another is this, see if you in this, you see a bunch of timings here, various timings. You need to have fine control of generating whatever timing you need for your receiver. Each receiver device has a different margin, and when you first bring your design and try to test, you want to tweak all these parameters at ease and try to test, right? So it is unavoidable, but you need to control all the timings. I'm not sure whether I have tried to list everything here, but you need control about everything, all the timing. Maybe sometimes even beyond what the spec is actually calling for, right? To get that first time for your error detector to initialize, right? People have spent weeks to get the error detector initialized. It's the first step. It's tough. So I thought I would want to just describe the most complex test in the receiver testing is, as you might all know, is a receiver jitter tolerance test. It kind of uses all the parameters, right? Try to use all the stresses needed, which is accommodated for in the design, and try to create a stressed signal which with which you want to test the margin the receiver has or whether it performs well. So this is, I think, more or less the test procedure in the CTS currently. First, you would do a rise time control. The waveform output from the waveform generator, you would slightly control the rise time. Okay, and then insert the standard reference channel. So you see an eye diagram which is slightly closing. The aim is to get to this diamond closing, right? And then add DJ, further DJ, so that you can close and try to reach this height and width and try to touch this eye diagram. So this would be a stressed eye. And further, you would also want to do some static skew, which is also in the spec, and it needs to have a certain DC common mode and SSC. So it's a very involved test with multiple iterations, right? To generate, you cannot generate this at one shot. There is a generator, there is a scope. You go on adding various impairments and this thing and observe what is happening on the scope. It's an iterative process. Of course, there are software available which helps you to automate and do this with a minimum intervention. So again, talking about test modes, right? So what's the first, in testing a receiver, what is given that your design has an error detector, right? Now I think moving from 1.5G onwards, I think having error detectors in the receiver to help testing is going to be the norm. So the first big challenge is how to put the receiver, the error detector on the receiver to initialize the error detector. You have a test equipment, you're trying to generate the waveforms, the amplitude, the stop state, the LP00 state to what your design is capable of. I've seen cases where the receiver needs to have a HS, the LP to HS transition, and then provide a sync, the HS sync, and then loop the PRBS. Right? This is one way to do it. It takes a lot of effort to challenge. I think even simpler way people are considering doing it is to have a design where you can just initialize with just a HS only pattern. Now, why I'm going away from LP is you think about the termination board now which comes into place, right? When you want to have both LP and HS fed, you would have one more fixture in between, right? You have a generator, you have this termination board. It adds additional complexity in testing. Of course, it can be done. I'm saying I think all the designers should keep note of all these points. I'm sure there are many more, to make the testing as easy as possible and as quick as possible. Right? This is one aspect which you can definitely consider. I also know that people are already working towards it, some cases. Another one is to get that calibrated eye which we saw, right? We could do in two ways. Either embed the channel on the generator and try to generate a stimulus. Or even better would be to have a replica trace in your board. This is actually a screenshot from one of the CTSs. Can't remember which one, right? Essentially, you connect your generator here. This trace exactly replicates what it has in your design, and you take this out and connect to the scope, okay? And then now you calibrate and get that eye. So after calibration, you feed this input to your design and test. So this would be more accurate and I think a more realistic data you would get out of this. So I think this is the last slide of my presentation. So all the content from my presentations are 90%, 99% derived from the CTSs and the spec. Okay. What was the next slide? Yeah, I hope you guys had a chance to visit the various exhibits in the booth, and I think it's now time for questions. I'll be happy to take any questions you may have. Yeah, sure. You may want to wait till the mic for a second so that everybody else can hear.
Hang on.
On slide 11 and 22, you mentioned that RX testing. Let me see. For receiver LP mode requirement, you are mentioning input pulse rejection and peak interference. First, would you explain a little bit more what they are and when that happens?
Sure. Here, I think this one, right? Yeah, it's maybe repeated in...
yes, either this one
yeah,
or...
okay. So to make... I'm not a designer, right? I'm a test guy. So I'll tell you my take on it. To make the LP receiver as robust as possible, the spec has specified these impairments or stresses to be tested with, to make the LP receiver more robust. The kinds of the stresses are, I will go back to that slide, I think it had a picture in it. This one. Okay, so that the receiver can work in the presence of interference and noise. And these are the noise the receiver should be able to tolerate. One is the E spike, right? They've defined this spike. There is some parameter defined. We should be able to tolerate a certain area of the spike. Even, let's say, for example, this is a zero level. If you have a small spike like this, the receiver should be able to reject it. That's what it says.
When does that spike
happen?
Yes.
Is what is your question. I'm saying in designs, I think there are scenarios in which it happens. There is change in termination. See, this is not a designer's answer. If anybody else in the room has a better answer, feel free to jump in. In LP receiver design, I think there are scenarios in which a spike can occur. There is terminations, change of termination happening. I believe those are the cases in which those spikes can occur. Yeah.
What's the peak interference?
Peak interference is just to make it robust against the RF interference. It would be just like an additional tone getting imposed on this, right? Let's say if we have this, I think I can. Let's say if we have a parallel clock lane, some clock lane is running next to it. There would be interference due to this lane on the LP lane. So this is common.
So like coupling or
yeah, they would call it crosstalk. Yeah.
On slide 21.
Sure.
I just try to understand the term.
Sure. Yeah, I will. I can't see the number. Okay, it's there at the right. Okay.
Spaced 1 hot. What is that?
Yeah, I will switch to the diagram to explain. Is there an easy way to get to the top of the presentation? Okay. So it's a type of encoding which the LP mode uses, where each bit has two subphases. Pardon me for a second, please. Yeah, here. So it's a type of encoding. Each bit has two subphases. For example, a bit 1, okay? A bit 1, this is bit 1, okay, from here to here, has two subphases. We call this as a mark phase, and they call it as a space phase. It's a kind of encoding. Okay? Does it help?
Can I ask other question? Have you conducted the conformance test for D-PHY products in the market?
So, yes, right? Yeah.
Many?
Yeah, D-PHY has been there, there for a long time, even before I started working on D-PHY, so it's been, yeah.
Are they meeting all the conformance tests?
I think,
I
right?
try to understand whether they are failing some requirements or kind of try.
Yes, I think in general, I would say yes. But I've heard concerns that this particular interference test, I'm not able to do it very well, right? If you want to just go back few years in D-PHY, there was always a challenge, very difficult to add these kind of stresses. Whatever we just talked about E-spike, right? It was difficult, challenging different boxes, adding together. So people had generally covered the CTS, but there would be one or two here and there where they would have to struggle with, yeah.
So, for test conditions you are able to make, what failures have you seen?
Let me see if I understand this question.
Failures
in terms of the device, on the device?
Yes, among many.
Yeah, it ranges a lot. I mean, there are many such instances. Almost anything and everything would be a problem. What happens is they first connect the scope, everything, and see some problem, and they would go back to the design and slightly tweak the parameter or extend the margin of some of the parameters, and then test again. Right? It's not a one-day match effort. Right? It goes on for weeks, and if not months.
So after fixes, they were able to meet all the.
Yes, in general, yes. Yeah, I would say yes.
Okay. Thank you.
Yeah, you are welcome. Thank you for the questions.
Any other questions for Partha? All right.
Okay.
But thank you very much.
Yeah.
Appreciate it.
Thank you. And if anybody wants to have further conversations on the same topic or with respect to Tektronix, I would be happy to engage. Thank you. Thanks for your time.
Thank you.